first.
So how many people got a chance to do part 2 of the Lab 1 notebook, which we recommended that you guys check out? Okay, yeah, no one. Yeah, that's fine. We were gonna go over it. Yeah, I figured we probably should. Yeah. Do you have it up?
Yeah. I have it open right here. So we'll start on part 2, and what this is this is building an AND gate on an actual quantum computer. So this seems pretty cool. Let's start it up. All right, are you guys able to see my screen? Cool.
Yeah.
All right, so let's start with lab 1 part 2. So here our goal is to execute an AND gate on a real quantum computer. So that's going to be like a device that's somewhere in the world that IBM has built, and we have remote access to this. And part of this is also going to be how you can set up a program or how you can set up your account such that you can do this as well. So in this tutorial, we're going to be executing an AND gate. And in part 1, we made an AND gate from different quantum gates. That was 2 weeks ago, and executed it on what we know as the qubit simulator. And here in part 2, you'll do it again, but instead, the circuits will be run on an actual quantum computer. Here, give me a second, let me just collapse this. And when using a real quantum system, one thing you should keep in mind is that present day quantum computers are not fault tolerant, they're noisy. And so what that means is in many quantum systems, a lot of them are prone to error, to outside variables, outside environmental factors. So quantum computers have to be treated very carefully. And that's why if you've ever seen a picture of a quantum computer, it's typically in a lab where people are wearing lab coats, and people take a lot of precautions when handling quantum systems. So it's pretty important that to make sure that you can have these devices as accurate as possible. And that's one active field that we are working towards, that all of us as quantum computing scientists or engineers. And so the noise in a quantum system is the collective effects of all the things that should not happen, but nevertheless do. Noise results and outputs are not always what we would expect. There is noise associated with all processes in a quantum circuit, which comes from preparing the initial state to applying the gates and finally qubit measurement. So for the gates, noise levels can vary between different gates and between different qubits. CX gates are typically more noisy than any single qubit gate because controlled NOT gate involves multiple qubits. So here we will use the quantum systems from the IBM quantum experience. If you do not have access, you can do so here. So now that you are ready to use the real quantum computer, let's begin. And so first we want to choose our device. And to do this, we need to load our account. So if everyone could actually take a second on their computers, if you guys are able to, I would like if you guys could go to IBM Quantum Lab, the Quantum Experience, and open up this Lab 1 notebook and just run everything that you had previously from the top. But then when you get down here, check to see if you can load your account details, if this box can run successfully. I'll give everyone a minute to do that. Is there anything else you wanted to add, Ajit?
I think maybe one thing I wanted to add was so when you guys are programming these, I think one piece of advice I have is to try to use like, I mean, it says it right there, but also just from my experience, like you can, if you can do something with like if you think you can do like something with more single qubit gates, like just try to avoid a lot of CNOT or any operations that involve like crossing over between multiple gates, because those computations tend to be noisier. So yeah, I mean, it says it there too, that CX gates are typically more noisy than any single qubit gate.
Right. And when you guys are ready, just type in the chat saying I'm ready. Check the chat real quick. Okay. You ready? Okay, I see Benjamin is ready. Don't worry. Are you sure, Hung?
Yeah.
Okay. Okay. Alex is ready. Starvation, are you doing all right?
Yeah, we can go ahead and move on.
All right. All right, let's go on ahead then. And so everyone that has gone so far, does it provide like a little message down here saying account provider for IBM Q is equal to, or for IBM Q, hub equals quote IBM dash Q, group equals quote open, and project equals quote main? You guys see that? All right, so if you guys see that, that means that, you know, you are able to load your account and you can actually run your experiments on a real quantum computer. And IBM.Q providers is another line that does, well, it allows you to look at all the providers that, you know, you can use. And what a provider is basically is a device. It's a platform somewhere in the world that allows you to run your experiment on a real quantum computer. And so this next command allows you to look at a list of all the quantum computers that you can run your experiments on. So it shows you a list of backends that are available. So we have this one in Armonk, we have one in Santiago, we have one in Bogota, Colombia, we have one in Lima, Peru, we have one in Belém, and we have one in Quito, Ecuador. So we have all these physical devices that we can actually run these experiments on. And then these four are all simulators, which we will get to soon enough, and we'll see what all of these simulators will do and their capabilities. But for now, we'll be running it on a real quantum computer. And so the choice that IBM has made for this experiment is running it on the one in Lima. So you can set a backend equal to the provider and getting the backend, which is in our case, the one in Lima, the quantum computer in Lima. And if we want to just run the backend_ex command, call it, we can see several details actually about this quantum computer, such as the number of qubits it has, and as well as how many jobs are pending, and several other details. I'm not sure if I recognize a lot of these. Do you recognize any of these, Ajit?
Oh wow.
Yeah, there's a lot of details, right? And I know this is a qubit configuration of sorts, but I'm not quite sure what it's used for. I know I was in the FRI quantum computing class and they talked about the different configurations of qubits, but I don't quite remember what it's for. Do you remember Sarvesh when he talked about this?
I think he might be away
Okay,
AFK.
that's fine.
Yeah,
That's fine.
I'm pretty sure it's the topology of the circuit. So you can only have coupling between nodes that are connected. So for example, if you need to do a C naught between 0 and 3, you need to first swap 3 with 1, and then you can do the C naught.
Oh, that's
Yeah.
interesting. I see what that is. Okay. I actually didn't know that. So this is what the qubit coupling is. I see. That's actually very interesting. So this is just the configuration, and you can look at some other things such as the properties of them. You can actually look at the frequency at which these qubits are ran at. And you can also look at several attributes in this case. And this is what the interesting thing is about these quantum computers is that, you know, you can see which machine can suit the needs for your project. So one good practice to always do is if you are going to run a device or if you are going to run a program on a real quantum computer, you want to check to see the specifications of the quantum computer to see if it suits the needs of your project. So we're choosing Lima in this case. And for our AND gate circuits, for our AND gate circuit, we need a back end with 3 or more qubits, which is true for all the real systems except for IBM-Q RMOC. And below is an example of how to filter the back ends, where we filter for the number of qubits and remove the simulators that don't suit our needs. So we can run this. So the ones that suit our needs are Bogota, Lima, Belém, Quito, and Manila. And another way we can check, another interesting thing we can do is we can choose to see which device actually is the least busy. So if you need to run your job really quickly, or you're under a time crunch of some sort, or you just purely want to check for efficiency of your algorithm, one convenient way to do that is to see which quantum computer is actually the least busy, which one has the least pending jobs on it. And so this function to get the backend with the lowest number of jobs in queue can be used. The downside is that the result might have relatively poor accuracy because, not surprisingly, the lowest error rate systems are the most popular. But nonetheless, it can show you which ones are available. So you can run this. And wait for it. So we see right now that IBM Q Manila is actually the least busy. And it gives you the configuration, the qubit topology, and all the other properties. And so real quantum computers need to be recalibrated regularly, as with a lot of quantum systems, and the fidelity of a specific qubit or gate can actually change over time. Therefore, which system would produce results with less error can actually vary. And in this exercise, we select one of the IBM systems, IBM Quito. So let's try this. So we are calling this as our current backend. And for step 2, we want to define the AND function, which we built previously with a real device. We now define the AND function, and we choose 8,192 as the number of shots or the amount of times that the circuit is run, the maximum number of shots for IBM systems, to reduce the variance in the final result. And related information is well explained here. So we use this thing called a Qiskit transpiler to help in running the circuit. And it says over here that it's important to know that when running a circuit on a real quantum computer, circuits typically need to be transpiled for the backend that you select, so that the circuit contains only those gates that the quantum computer can actually perform. Primarily, this involves the addition of swap gates, so that 2 qubit gates in the circuit map to those pairs of qubits on the device that can actually perform these gates. So let me read that last sentence. Primarily, this involves the addition of swap gates, so that 2 qubit gates in the circuit map, 2 qubit gates in the circuit map to those pairs of qubits on the device that can actually perform those gates. And the following cell shows the AND gate represented as a Topology gate decomposed into single and 2 qubit gates, which are the only types of gate that can be run on IBM hardware. So over here is our AND gate. So that's the CCX gate. And this can be transpiled into just 1 and 2 qubit gates, since this is a 3 qubit gate over here.
Yeah.
That looks
So
slightly
basically,
better.
it doesn't actually have 3 qubit gates. It's just emulating that with a
Okay.
bunch of 1 and 2
Yeah.
qubit. Yep.
Wait, sorry, could you repeat that one more time, actually?
Oh, I was just saying, you don't actually have 2 qubit or 3 qubit gates in this system. So like, I mean, yeah, I think that's just what makes it interesting, which is that like, we're just
Okay.
going to use 1 and 2 qubit gates to emulate a 3 qubit gate.
Exactly.
Yeah.
Yeah,
This
so
is
this is
related
just,
to, oh, sorry.
oh,
I was just going to say this is related to the topology that we saw in that graph earlier,
mhm.
where you couldn't do a CNOT between 0 and 3. So that's why they're introducing swap gates, because they need to get the qubits close to each other before they can do 2 qubit operations. So,
Yeah.
Right.
I think this is
So-
interesting for, oh, sorry.
No, you go ahead, I'm sorry.
Yeah, I was just saying, I feel like this is also kind of interesting when you think about like universality of gates, because I feel like it shows that you don't need any 3 qubit gates because a 3 qubit gate you can make with 1 and 2 qubit gate. So
Decompositions of these gates are interesting to see how they're made and how these operations are carried out.
also, just to add one more note, IBM was running a competition, I think a year ago, where they were trying to improve the fidelity and efficiency of their swap gate procedure. And the reason why that's so important is this, because they have to transpile circuits and they get like thousands of swaps in order to get qubits nearby. And so the swap gate can be a really big factor in how long your algorithm takes on their computers. So
yeah,
Right.
some cool facts.
So just a quick question. What exactly does transpiling mean?
It's basically like, so yeah, you go ahead.
oh, I think, did anyone want to give any thoughts, like non-officer people first? Okay. Yeah, in that case, you go ahead, Ronak.
Yeah, so it's sort of like compiling. Like compiling takes a program and turns it to assembly. Transpiling is just the fact that every single machine, every single quantum computer IBM has a different architecture. And so you can't just compile to OpenChasm, which is like the quantum assembly that IBM uses. You have to transpile to the specific gates that you can do on this quantum computer, this specific quantum computer. So it takes your circuit and then it computes a different circuit that's equivalent. It'll do the same things, but it only uses valid operations. So there's no CNOTs from 0 to 3, right? Because you can't do that on that previous computer. It would have to introduce swaps so that it's only the CNOTs that you can do.
Wow, that's actually really interesting. Actually,
So you're
that
never
is-
actually running the circuit that you tell it to run. You're running one that's equivalent that can actually run on the device. So
I actually didn't even know that. What I'm interested to do, like as a side thing, and I recommend you guys do this too, is you guys play around with these different backends. Like what you do is you can insert Quito or any of these other backends that we have up here. We have Lima, we have Belém, we have Manila, we have all of these. And we also have Bogota. You can try experimenting with all of these different backends to see the differences in the circuits that come out of them due to the topology of their qubits.
yeah, there's a transpile function where you can see what the transpiles do. Otherwise, you'll never see it. They'll never show you what it transpiles to unless you like call the function and then print it out and see what the circuit looks like.
That's actually really cool. I didn't even know about that. I'm definitely going to play around with that later. That's awesome. So
the house function is useful just to see like what your output might look like.
wait, sorry, could you say that one more time?
Well, I was saying you can just see what your output's going to look like with the transpile function.
Oh, okay.
Yeah. Or yeah.
Is there a way we can call that? Here, let's go on for now and let's see how we can output what the function will look like with a transpile function. But in addition, there are often optimizations that the transpiler can perform that reduce the overall gate count and thus the total length of the input circuits. So one important thing that many quantum algorithms are designed to do nowadays is that a measure to see how efficient they can be is the actual depth of the circuit, which is how many gates you use to carry out a specific operation. And so over here, what the transpile function can do is that one of the operations it can do is actually reduce the overall gate count, hence making a more efficient algorithm or a way to do something, and thus the total length of the input circuits. Note that the addition of swaps to match the device topology and optimizations for reducing the length of a circuit are at odds with each other. In what follows, we will make use of initial layout that allows us to pick the qubits on a device used for the computation and optimization level. An argument that allows selecting from internal defaults for circuit swap mapping and optimization methods to perform. So first, let's modify the AND function in part 1 for the real system with the transpile step included. So what we can do over here right now is just run this cell and then this cell and see what the output comes to. Or that's just a subroutine, so it's not going to really output anything. When you submit jobs to quantum systems, job_monitor will start tracking when you submitted your job, where you submitted your job in the pipeline. So it'll tell you what number your job is and how long it could take to run the experiment. So first, let's examine the IBM Quito through the widget by running the cell below. So first, even though this has appeared a few times now, we can look at the device topology. So we can see that 0 and 1 are interconnected, 1 and 2 are interconnected, and the different connections of these devices can show us which qubits we can run with different gates. So that's basically what that is. And we have to determine the 3-qubit initial layout considering the error map and assign it to the list variable layout 2. So hold on. That's weird. Okay, that's really weird. Real quick, guys, I don't know why it's saying this, but I think this meeting is going to end in less than 10 minutes, like 9 minutes it's gonna end. And I have to upgrade the Zoom thing. I don't know what that is. So should we end this meeting in 10 minutes or should we move this somewhere else?
No, we can just rejoin the meeting again.
Okay.
I've heard people do this when they don't have Zoom licenses. That all Zoom meetings just kind of last for 40 minutes and then you have to restart them.
Okay.
Oh yeah.
That's pretty
Aditya,
weird.
do you have 2 Zoom accounts? Because it seems like you're using your non-UT one right now.
Does it? Wait, hold on.
Yeah. Try logging in through UT because then you get unlimited length meetings.
I thought I am using my UT account. That's weird.
Are you using your personal ID? Because the link here says like US3 whatever instead of saying UTexas in the Zoom link.
That is really weird because when I log into Zoom, it does say that I'm using my UTexas account.
All right, we can talk about it afterwards, but for now we'll just
yeah.
rejoin.
We'll figure this out later.
Sure.
But anyway, so first what we got to do is determine the 3-qubit initial layout considering the error map and assign it to the list variable layout 2. So where exactly is layout 2 happening? It's not, that's kind of weird. So we need a 3-qubit initial layout here, and we just need to list the 3 qubits that we're going to use. So in this case, what we can do is use, we can use thinking we can use 0, 1, 3. Do you second that, Ajit? All right, let's just try 0, 1, 3 for now. And describe the reason for the choice of the initial layout. So from what we can see over here, 0, or we could do 0, 1, and 2 in that case. I'm playing around with this and trying to understand what the reasoning is. Let's see if this runs. Oh, it's queued. So right now we see that the job is queued as 1. So this job is currently running and then it'll output soon enough. So the job status is still being queued. So this is going to run 4 times, and then we're going to see the probability of the correct answer for input 0, 0, 0, 1, 1, 0, and then 1, 1. It's almost done. All right, so the job is finished running and we can see the probabilities of the correct answer actually for these inputs. So if we have the input 0, 0, we have a 93% fidelity rate. For 0, 1, we have a 95% fidelity rate. For 1, 0, we also have a 95% fidelity rate. And for 1, 1, we have a 90% fidelity rate. So it also prints out the highest of these probabilities and the lowest. So 95 is our highest and 90 is our lowest. So before we continue, I'll basically explain what this code block does. So we have all our outputs. So hold on, let's break down this part first. So it goes for each of the qubits. So we have input 1 as qubit 1, and this can be 0 or 1. And for input 2 as qubit 2, which can also be 0 or 1. And we have our QC transpiler, and our output is equal to our AND gate, which we previously made, equal to our and the variables that we're tagging are input 1, input 2, the backend, which is IBM Quito, and the layout. And so all of our outputs, so output underscore all, which is our array up here, we are appending our output, and our QC transpiler details we are outputting over here. And from this, we can actually get the probabilities of all the inputs we're inserting. So first we print out the probability of the correct answer for our inputs, and then we format the actual probability. And our worst and our best are assigned over here, and these are the worst and the best. So what this code block basically is doing, it's running all the probabilities for our circuit and then printing out them. So from here, what we can do is we can interpret the result. And so there are several quantities that actually distinguish these circuits. And chief among them is the circuit depth, which we previously talked about. The circuit depth is defined in detail here. So if you want to read more about circuit depth, you can always go to this link or this link and click on the quantum circuit properties tab. Circuit depth is proportional to the number of gates in a circuit and loosely corresponds to the runtime of the circuit on the hardware. Therefore, the circuit depth is an easy to compute metric that can be used to estimate the fidelity of an executed circuit. So the less operations you have overall, the higher the fidelity goes up. And a second important value is the number of non-local multi-qubit gates in a circuit. On IBM quantum systems, the only non-local gate that can physically be performed is the C0 gate. Recall that C0 gates are the most expensive, computationally expensive gates to perform. And thus, the total number of these gates also serves as a good benchmark for the accuracy of the final output. And we'll run circuit depth and result accuracy in a minute. I think this meeting is about to end, so I'm going to end it right here, and you guys can rejoin and we'll continue this meeting. All right, see you guys in a couple minutes. Okay, so this is the second part of the session on Feb 26, and real quick, what we can do is, if you guys want to access any of the materials in for learning labs, you can go to this link right here, which I will pin in the messages. And you guys can access this for whatever materials or whatever recordings we have. So if you go to this link, you can see the first session that we have as well as the intro slides. And I'm going to upload both of today's recordings onto here. So anyway, let's finish off the first part of lab 1. or the second part of lab 1 by looking at the circuit depth. So if we want to look at the AND circuit for IBM underscore Vigo with input 0, 0, we can actually test this result. So the total circuit depth is 21, considering all the operations that it has over here in this final measurement, and the number of non-local gates is 15. So that's for 0, 0, and the probability of the correct answer is again 0.93. And so let's test out for 0, 1. So we have the circuit depth is 22 because there is an additional NOT gate over here on the first qubit, and the number of non-local gates is 15 again, and the probability of the correct answer is 0.95. So let's try for 1, 0. Okay, and same thing goes for over here. The NOT gate these should be swapped. This should be up here, and this should be down here. But anyway, they would give a similar result with a similar circuit depth and number of non-local gates with a similar probability of a correct answer. And finally, we can test the output of 1, 1. And so we see both of them over here have NOT gates. So it still has a total circuit depth of 22 because these operations happen at the same time. That's another important thing to consider when the operations happen. So for example, how you measure circuit depth is how many operations occur at a single time. So these two happen at the same time, that's one layer. And since this one happens at another time, that's another layer. This is a third layer, this is the fourth layer, fifth layer, and these two happen at the same time, so they're the sixth layer, and so on and so forth. So that's how we measure circuit depth in this case. And now what we can do, now that we see all of these details, we can break down what each of this means. So actually, no, I already wrote this down. Okay. So finally, we can explain the reason for the dissimilarity of the circuits and describe the relations between the property of the circuit and the accuracy of the outcomes. So does anyone have any ideas as to why, as to the reason for the dissimilarity of these circuits? And also between the relations between the property of the circuit and the accuracy of the outcomes. Does anyone have any thoughts or ideas for that question?
So all the circuit depth and also it's actually not the same. No, I really don't know.
Yeah, it's quite difficult. But the point is when you construct a circuit, use as few non-local gates as you can and use as little of the circuit depth as you can. And what that will allow you to do is have an operation that can run fast and have it run accurate. So that is all we have for today. Is there anything else we need to do, Ajit?
Oh, I didn't realize I was muted. No, I think, yeah, that's that about like covers it. For next time we can, I don't know, we could like just go over these concepts one last time if you all want, or we could move on.
Or we can start on lab 2.
Yeah, like, but it does kind of feel like, I mean, just based on like the absence of questions and much response from y'all, it does kind of, I don't know, do y'all think you'd prefer that we go over these again, like just, talk more about,
Like-
this, just this basic, like how the computer works, like how IBM's computer works. I think I did a great job of explaining like all the different details that go into it. We could do more of that.
I'm kind of all over the place, so sorry if I am confusing you guys, but if you guys have any questions ever, don't be afraid to interrupt or speak up whenever you want and ask whatever question you want.
I think it would be good to, I think you explained it fairly well today. Um, I think it would be good to go to the next lab. Um, this is just more of a general administrative question. Does the quantum collective as a whole have any plans to move its meetings to in person anytime soon? I mean, I do find it easier to pay attention that way. So,
You do? Okay. Thank you for your feedback, first of all. To tell you the honest truth, I do not know of a plan that has been set in place for this, but I will surely bring it up to other officers. Ajit and I will bring it up to other officers and see when we can move this stuff in person and start having these meetings in person, and also to see where we can book them.
Yeah, I think so. Booking is not actually as big of an issue.
Okay,
I think the bigger thing is just coordinating with other members and other groups in the club. Like I
right.
think the reading groups are online and they always have been.
Mhm.
And you know, like um I don't know if they have plans to move in person, like um but yeah, you're right. I think I agree with you that it's easier to pay attention. So we could make that decision. We can do a poll or something too,
Yeah,
because there's also the flip side of we might get less people if we do in person because it's less convenient. You know, you can't just log in from anywhere. You have to be at a certain place at a certain time.
right.
that is fair. Yeah, it is. It could
Like
be
I'm
hard.
doing this from home right now, but yeah,
Yeah, like for example, yeah, like if we try to do this in person, if like it's more unlikely that they would be able to, you know,
I
or
mean,
like I think yeah,
I'll find a way to get there regardless, but still, like, whether you
yeah,
guys prefer in person or online, we'll get a collective poll going and see what we can do about it. Thank you for your feedback.
All right. Thank you.
yeah. All right, if there are no more questions, then y'all have a great day.
Cool. I will stop the recording and upload this.